Ever tried pushing a heavy box across the floor and felt it stubbornly resist your efforts? It feels like something is pushing back, doesn't it? That's a battle of forces, a constant tug-of-war happening right before your eyes. A force, in its simplest form, is simply a push or a pull. It's an interaction that can change an object's motion. When you push the box forward, friction, acting against the direction of motion, pushes back, trying to slow it down. Forces are absolutely everywhere, governing everything from the precise impact of a soccer kick, determining the ball's trajectory, to the majestic dance of planets orbiting the sun, held in place by the immense gravitational force. Even when you're standing perfectly still, gravity is constantly pulling you down towards the Earth's center, while the ground beneath your feet exerts an equal and opposite force, pushing you up, preventing you from sinking. This is called the normal force. These invisible pushes and pulls constantly interacting shape our world and dictate how everything moves or doesn't move. But how do we make sense of all these forces acting at once, often in complex and confusing ways? Scientists recognize the need for a clear and concise way to visualize and simplify these complex interactions, allowing for easier analysis and understanding. That's where our amazing tool, designed to help you unravel the mysteries of forces, comes in. Let's dive into a fundamental tool in physics, the free body diagram, often abbreviated as FBD. It's a cornerstone for understanding forces in motion. The first step is to draw the object of interest by itself, isolated from its surroundings. Think of it as extracting the subject from a photograph. Then carefully add arrows to represent every force that is acting directly on that object. These arrows are vectors, indicating both magnitude and direction. The beauty of the FBD is that it's the best way to break down complex, real-world situations into manageable components. It transforms intricate scenarios into simple, clear sketches, making the underlying physics much easier to grasp. FBDs are incredibly useful because they help us apply Newton's laws, especially the famous equation F equals sine ma, which relates force, mass, and acceleration. By meticulously drawing all the force arrows, we create a visual representation of all the influences on the object. This allows us to easily see which forces work together, aiding the motion, and which forces oppose each other, hindering the motion. What are some common forces you'll encounter? There's gravity, Fg, always pulling downwards, the normal force, Fen, which acts upwards from surfaces supporting an object, friction, F, which always opposes motion, and tension, Ft, which is the force exerted by ropes or strings. Each force gets its own arrow on the diagram, showing its direction and often its relative strength or magnitude. Longer arrows typically indicate stronger forces. When creating an FBD, we intentionally ignore extraneous details like color, texture, or background elements. We just focus on the essential forces. This deliberate simplification is the true genius and power of the free body diagram. Think of it as your personal blueprint for understanding and predicting motion in any physical system. Ready to draw your first FBD? Here's how. Step 1. Isolate the object. Draw it as a dot or box. Step 2. Identify and draw all forces with arrows pointing outward. Gravity, arrow down. On a surface, normal force up. Rope, tension, sliding. Friction opposes motion. Step 3. Label each arrow. FG, FN, F, Ft, or F _ push. Step 4. Check your work. Are arrows correct? Labels clear? Add an XY axis if needed. A quick review prevents mistakes. That's it. You've made a professional FBD. This skill unlocks the power to analyze any physical situation. Alright, let's put our knowledge to the test and try a few examples. We're going to walk through some common scenarios where you can apply the principles of free body diagrams. Remember, the key is to break down complex situations into simpler, more manageable force representations. First, let's consider a box sitting peacefully on a flat floor. This is a classic starting point. The first step is to draw the box itself. This represents our object of interest, the one we're analyzing the forces on. Gravity is always present, pulling the box downwards. We represent this with a downward arrow, labeled Fg, for the force of gravity. But the box isn't falling through the floor, is it? That's because the floor is exerting an upward force called the normal force, Fn. Since the box is stationary, not moving up or down, we know that these forces must balance each other out. They are equal in magnitude and opposite in direction. Now let's add a bit of complexity. Imagine we're pushing the box to the right, but it's moving at a constant speed. We add an arrow pointing to the right, representing the force we're applying, F_ push. But the box isn't accelerating, so there must be another force opposing our push. That's friction, F, pointing to the left. Because the box moves at a constant speed, the pushing force and the friction force are equal in magnitude, resulting in a net force of 0 in the horizontal direction. Next, let's tackle a box sitting on a ramp or an inclined plane. Gravity still points straight down, always towards the center of the Earth. However, the normal force is now angled, perpendicular to the surface of the ramp. And if the box isn't sliding down the ramp, static friction is acting, pointing upwards along the ramp's surface. While each scenario might appear different at first glance, the fundamental steps for creating a free body diagram remain the same. Start practicing by visualizing the forces acting on objects all around you. A book resting on a table, a chair supporting your weight, even yourself standing on the ground. Try to imagine the FBD in your mind. What forces are acting on the object, and in which direction are they pointing? The more you practice visualizing and drawing these diagrams, the more intuitive and second nature it will become. Drawing FBDs isn't just a task for your physics homework assignments, it's a powerful tool for understanding and visualizing the often hidden forces that are constantly shaping the world around us. So, pick up a pencil, grab a piece of paper, and start drawing those free body diagrams. Because science, and especially physics, is truly everywhere you look.